Hello everyone, this is the BNB Chain Club, and today we're continuing on the series to build a real-world crowd sale on BNB Smart Chain that can be used to raise funds in a real-world ICO. Today's video is part 2 of the series where you will be learning the fundamental concepts of Solidity programming by writing and testing a given set of Solidity codes. Do check out part 1 if you have yet to do so to set up your environment. This video will give you the opportunity to compile and test the following sample Solidity codes in the Remix environment. And without further ado, let's get started on your second lab. The understanding of Solidity data types. Solidity is a strongly typed language, so every variable has an associated data type. In this section, you will be practicing some of the commonly used data types in Solidity. You can copy and compile the given code in our GitHub repo in the video description below and follow along. First, let's create a new remix file named mydatatypes.so and copy the code from our repo into the file. Notice that the keyword public is used so that the variables can be accessed by outside the function and contract. In this code, we are basically creating different variables of different data types such as string, boolean, integer, and unsigned integer, and assigning its intended value to the variable. Allow me to introduce you to all the different data types. First, the string, which is a sequence of characters. Some example would be hello, BNB, hi there, chocolate, or any kinds of sentences that you can think of. Second, the boolean, which is a boolean value that infers to true or false. Third, the integer, which can be a negative or positive integer that has no decimal. Example, 0, negative 30,000, or any large whole number. The fourth, uint, which means unsigned integer that indicates only positive number with no decimal. There are 4 types of variation in bits width. The uint8, which means unsigned 8-bit integer that gives an output range of 0 to 255. The uint16, which means unsigned 16-bit integer that gives an output range of 0 to 65,000. The uint32, which means unsigned 32-bit integer that gives an output range from 0 to this large amount here. The uint64 that gives an output range of 0 to an even bigger amount. Fifth, the fix, which means the fixed point number, which can be a negative or positive number with a decimal after it. An example of it would be 20.00.1, or it could be negative 42.4242. Meanwhile, ufix, which indicates the same as uint, which means only positive number with decimal. 3.14, it can be 10.01, 25.19, but not a negative decimal value. Lastly, we have address, which is in hex format that has methods tied to it for sending money, and it mostly looks like this here, which is similar to your wallet address in hex format. So the code will demonstrate the different Solidity data types explained. So let's go ahead and make sure our compiler version is valid to what we have selected, and the auto-compile function should help you to auto-compile your code automatically. Next, let's deploy our contract and check the outcome of our contract. So we can just select a wallet that Solidity has given to us. We hit deploy. Right, over here we can see that our contract has been deployed successfully. Let's take a look into our contract. What we see here is all the variables that we have created in our code, and what we can do and click on each of them to take a look at what is being assigned to this particular variable. Alright, so my bool, we have a value called true. My integer, we have -1. Same for my uint, a value that we have set in our code, so on and so forth. And that is all for an introduction to Solidity data types. Adding two numbers. In this code, you will learn how to import a math library into a Solidity code and add two numbers of the same data types using the library function called savemath.add. Let's create a new file in Remix called calculate.so and copy the code from our repo into this file. Pay attention to line 3 here, that is importing the library of SafeMath from OpenZeppelin. Many contracts can use functions in the library. If you have many contracts that have some common code, then you can deploy that common code as a library and let people use it. What SafeMath library does is that it helps you to check for specific errors such as divide by 0 and prevent buffer overflow. Within this library here, SafeMath, there's many predefined arithmetic functions for you to call to perform calculation, so you don't have to write your own formula and functions to do calculation, such as try add, try sub, try divide. I will go more in depth on OpenZeppelin libraries in part 3 of this series, so as for now, let me show you how we go about leveraging on the SafeMath library in our code. In this code, we first create a variable called value that is of type uint256 and a function that takes in two parameters of type unsigned integer, value 1 and value 2, and add these two positive numbers with no decimal using the add function that is given by the SafeMath library, savemath.add here. And the result of adding these two numbers is put into the value variable that we created. Now, let's deploy this contract and test the function. So let's go ahead to deploy the function. Select the contract, calculate.so, hit deploy. Our contract has been deployed. Let's take a look at the contract. Under the contract, we will input two numbers as the function parameters. So maybe I put 10 and 30 and then I hit add. Now we can check on the value variable. We should get a total of 40, which is the equal amount of 10 plus 30. So as you can tell here, instead of using value underscore 1 plus value underscore 2, we can simply just use the library function of savemath.add to do the arithmetic calculation for us, and that is how we perform our mathematical operations using the SafeMath library. Enum data type. First, let's create a new remix file named mystatus.so and copy our code into the file. The concept of enums restrict a variable to have one of only a few predefined values. The values in this enumerated list are called enums. The type enum is an enumerated type for which only user-defined values are permitted. Enum is explicitly convertible to integer types. The integer value of each enum is a zero-index order in its enum declaration. So in this case, red will have an integer index of 0, amber will have an integer index of 1, and green will have an integer index of 2. So in our code, when we create a variable called status value that belongs to a class of status, this variable here can only contain value that is predefined in this list. So any value aside from red, amber, and green is not allowed. So in our code, we have a constructor function that runs automatically when the contract is deployed to assign the value green from the enum list to the variable to status value. If we want to change the value of status value to other color, we will have to run the specific color function such as green, amber, or red to change the status values to other color. Now, let's deploy our code and execute the function and check the value of status value. So we will hit deploy. As usual, select mystatus.so, deploy, open the contract. Now, what we can do here is first check the status value. We should get the index of position 2, which indicates status value of it being green. Now, if I want to change it to red, I will press the red function and I'll click on status values to check again, and you can see that we get an index position of 0, which indicates red. String manipulation using arrays. In this example, you will store values of the same data type using arrays. Let's go through the code. We first declare an array of person type called people. An array is a data structure which stores a fixed size sequential collection of elements of the same type. We then create a variable called people count that is of type uint256 that is intended to store and give us the number of people in the array. Next, we define a structure called person that has the attribute of what a person has, which is their first name and last name. What this means is that when you create a person object using this structure, the object will contain the first and last name of the person. And in this function called addPerson, we are taking in two parameters of string type, the first name and the last name. And what we are doing in this line is we first create a person object here using the two parameters, and we use the push property of array to append a new element at the end of the array called people, where .push appends our newly created person object into our array, and it will also returns a reference to it based on its index position in the array that is being saved into the variable people count that we created. So let's deploy this code and first check out our people array. So we will deploy this code, open up the contract, click on people count. We should have an indication of 0 because currently there are 0 people in our people array. So what we do first is we will add a person, for example, David Chow. So click add. Now, if you click on people count, you have a total of 1 person in your array. Now what you can do is that at this people here, you can actually access within this array at index 0. It should give you back the person, first name and last name, David Chow. Now say we add another person name called Peter Lee. Click add. Now we'll click on people count. It should be incremented by 1 to have a total of 2 person in the array. Now in order to access the person Peter Lee in the array, we'll have to indicate the index position in the array, which is 1. Click on people, we should get Peter Lee. Counter using msg.sendo. In this example, you will learn the usage of msg.sendo through a simple Solidity code. So let's go ahead and copy the code here. Here we have a contract called counter that has the core functionality of a counter, which is to increment a count. So we have two variables, a count variable that is equal to 0 by default, and an owner variable of an address type to keep track of the owner address. If we take a look at the increment function here, the idea here is that when a function is called, msg.sendo is the account that calls the function, which is then checked against the owner variable that contains the owner address. And the counter, which is the variable count only, works and increment by 1 when the MSG sender is the same as that which deploys the contract, also known as the owner. So in conclusion, msg.sender is the account that deploys the contract and is stored as the owner. And in this contract will store the number of times the increment function has been called by the account ID that deployed the contract. Also, pay attention to this constructor for the class that is executed as soon as the class is instantiated. In other words, when the contract is deployed live. And lastly, the count function to return the value that is in the count variable. Now let's deploy our code with this account here and test the function. Take note, the very first one, this account address will be our message.sender, which is both the contract owner and also stored as the owner variable in our code. So using this address, let's deploy the contract, open up the contract, we should be able to execute the increment function and get a count value. But by default, prior to incrementing, our count value will be 0, and if I click increment, our count value will be 1. If I click it again, our count value will be 2. Now, take note, this address here is now our owner. Now if I switch it up to another address and try to increment, you will realize that my count will not increment. That is because it does not satisfy the condition where my owner is equal to my current address that I'm using. This address here is not the same as this. Therefore, there won't be any increment in the count value. tx.origin. In this example, you will learn the usage of tx.origin. tx.origin is a global variable in Solidity which returns the address of the account that starts the transaction. Using the variable for authorization could make a contract vulnerable if an authorized account calls into a malicious contract. A call could be made to the vulnerable contract that passes the authorization check, since tx.origin returns the original sender of the transaction, which in this case is the authorized account. Now you may be thinking, isn't this the same as msg.sender? Pay close attention to what I'm about to say. tx.origin and msg.sender are not the same. The tx.origin global variable refers to the original external account that started the transaction, while msg.sender refers to the immediate account that invokes the function. In simple terms, with msg.sender, the owner can be a contract. With tx.origin, the owner can never be a contract but a user account. In a simple call chain, we have, for example, contract A calls to contract B calls to contract C, and contract C calls to contract D. Inside contract D, message.sender will be contract C, but its tx.origin will be contract A. So the reason why tx.origin is vulnerable is because if D happens to make a call to a malicious contract called E, A, which is a user account, will suffer from it, and they may be suffer from attacks such as drainage of wallets fund. Therefore, most people try to avoid using tx.origin but rather using msg.sender, so that when you make a call to a malicious contract, it doesn't trace back all the way to a user wallet. So let's go through our sample code here. In this code, there is 3 contracts in one Solidity file. You can see contract C, B, and A. Let's go through what each contract comprises of. Contract C has a function called sendAddress, which basically just returns the address of tx.origin, which is also the very first original account that started the transaction. Contract B has a function called contract C, which first initializes a contract C. It first starts a contract C, and then it calls the function sendAddressed in contract C, right? c.sendAddressed, which will return the address of tx.origin. Contract A does the same thing as contract B, with the difference of it calling the function in contract B instead of C. This may look very confusing, but basically this whole Solidity file is trying to illustrate a flow where contract A calls to contract B and contract B calls to contract C. So at the end of the day, when we first call the function in contract C, it will return the account address we used to execute the function in contract C, as this is the very first original account, the tx.origin. And if we were to execute either contract A or B, it will also return the same account address as what we saw in C, and all this is due to the use of tx.origin. So let's go ahead and deploy our code to test it. Since we have 3 contracts, we will use 3 different accounts to deploy each of them. So the first address here to deploy contract A, second address to deploy contract B, third address to deploy contract C. Now first we'll open contract C up, and at this address, if I were to execute the function in contract C, I should get back the address that was used to call this function, which is this. Now, if I were to execute the function in contract A, which does the calling of contract B, and contract B does the calling of contract C. Ideally, the contract C must return the address of the contract B, but in the contract C, the variable tx.origin is used to return the original address. Thus, the variable tx.origin will return the original address that was used to call contract A and not what was being used in contract B. So if we were to use the fourth address here, 787, to execute call contract, we will get an output of 787, the address of this that was used to call at contract A, and not the address that was used to deploy contract B. And this actually showcases the flow here, whereby we use A, which calls to B, and B will call to C, but C doesn't return the address of contract B that calls contract C, but rather it returns the original address that started from contract A. Transferring of ICO. A transaction is an agreement between a buyer and a seller, a supplier and a consumer, or a provider and a consumer. Ethereum helps in executing the transaction. One of the types of transactions that can be executed in Ethereum is the transfer of ICO from one account to another. So let's take a look at the code we have here. What this contract does is that upon deployment, the constructor here will take in an address you specify when deploying the contract and set the address as the wallet variable. We also have a mapping called sender that keeps track of sender address and the number of times a sender transacts a transfer. This can be seen in the send ICO function, where upon call, an increment of 1 will be added to the sender record, and a transfer of the amount specified will be sent to the wallet address that we set up when we deploy the contract. So let's go ahead and test the code. We first copy an address from the account drop down here, and then we paste it in this field and we click the deploy button. Our contract has been deployed with our wallet being this address. Now let's open up this contract. Now we select another account address, and what we do is that we will basically input, let's say, an amount value of 20 ICO. What it does is that when we click on send ICO from this address, it will minus 20 ICO and transfer 20 ICO to this address, which is our wallet. So let's go ahead and test it. I will click send ICO. Now as you can see, our address has a decrease in minus 20 ICO, and our wallet has an increment of plus 20 ICO. And what you can do is that you copy this address, you paste it in here, and you click on sender. It will tell you that you have managed to transfer one time. Now if I were to do it again, now I put 10 ICO, same address here, I click send ICO. Now if I were to click sender, it will increment by 2, which shows us that this address transfer 2 times. Error trapping. Solidity provides various functions for error handling. Generally, when an error occurs, the state is reverted to its original state. Other checks are to prevent unauthorized code access. Some of the important methods used in error handling are assert, require, revert. I shall deploy the contract and explain the usage of assert, require, and revert with the code we see here. First, we have the require method. The require statement is generally used to validate conditions prior to execution, such as making sure an input value is more than or less than a value as seen in this code. If the condition is not fulfilled, the transaction will not go through and an error statement specified in the required statement will be shown. Let's test it out. So at test require, we have a required statement saying that the input of j must be more than 100, otherwise the error message of j must be greater than 100 will be shown. So if I were to put 90 and hit test require, it will not go through. It will result us in an error with the error message j must be greater than 100. So if we were to specify 120 and we hit test require, it will go through the condition and our transaction is successful. Now if I were to click on I should get a value of 120. Generally, you should use required most often, and it is used towards the beginning of a function. Next, we have the assert statement that helps validate state after making changes. It is used to prevent conditions which should never ever be possible. Generally, you will use assert less often, and it will mostly be used towards the end of a function. Basically, the difference between required and assert is that require should be your go-to function for checking conditions, while assert is just there to prevent anything really bad from happening after execution of code. So as you can see here in line 16, assert I is more than equal to j. This is a condition that will never happen. For example, if at j I input a value of 200, I will plus equal to 200, I will result in 200, and 200 is still more than or equal to 200, which is j. So basically our assert here is used to prevent conditions which should never ever be possible. I will always have a greater value or equal to j. It will never be lesser than j because it is a plus equal operation. Lastly, the revert statement handles the same type of situation as required, and it can be used to throw an error. So in this case, for test revert, we're taking two parameters, x and j. And what we do here is that we check if x is more than j, if this condition is fulfilled, it will throw out the error message of undoing state changes. So what this function does is that it's trying to ensure that x is never more than j. So let's try to make this happen. So if x we put 100 and j we put 50, x will be more than j, and thus this error should throw us out. Let's click test revert. The transaction has been reverted to the initial state, and the reason is being stated here. So in order to not have this, what we have to do is to provide an x value smaller than j. So let's change it to 50 and 100, and we click and it will be successful. And with that, we have come to an end to this video. I hope this video has helped you to learn the fundamental concepts of Solidity programming by writing and testing the given set of Solidity codes we have provided in our GitHub repo. I hope you are now more familiar with Solidity codes. If you have any questions or input, do comment at the comment section down below, and remember to like and subscribe. Have a nice day.